So I welcome all to this SimCenter community roundtable. This is hosted by the Uncertainty Quantification and Natural Hazards and Engineering Working Group. And title of this roundtable is going to be UQ approaches for computational efficient hazard vulnerability assessment at the regional scale. We have 4 excellent speakers. So how we're going to organize this, each of us is going to take 10 minutes to present on the specific topics that we have chosen. And then we're going to follow up with questions and answers, and also then follow up with a little bit broader roundtable discussion. So while we present, we're not going to hold for questions. We're going to do the questions after all of us, 4 of us has presented. Please use the Q&A feature of the Zoom, not the chat feature, to ask the questions. And then at the end, we're going to prioritize some of them, and we'll have time also for some greater discussion. So our 4 speakers are going to be myself, Alexandros Taflanidis, Paolo Bocchini, Jamie Padgett, and Abdullah Safizadeh. Before proceeding to my talk, I will try to motivate a little bit more the roundtable discussion. And I will start with a quick overview of the regional UQ challenges. To classify these challenges, I will come and view the risk as a convolution of exposure, vulnerability, consequences. So in this case, the hazard exposure needs to address the whole region. The vulnerability needs to consider a very large number of assets. And the consequence, again, need to figure out the consequence across the entire region. So the key attributes of these components is you have a correlation across many spatial locations for the hazard, computational complexity for simulation of each scenario, and also you need to explicitly and consistently actually address the aleatory hazard variability. And for the vulnerability, the information fidelity becomes important because you need to create a very large number of models. Again, computational complexity is still critical because you have a very large number of assets that you need to simulate the response for. And again, since you have this aleatory hazard, efficient propagation of the aleatory variability is important. And finally, for the consequences, against double correlation across the whole region, but also correlation of properly propagating the aleatory hazard. And you need to do some type of network analysis, again, great computational complexity. So the UQ challenges that this setting comes and creates, computational efficiency really critical. You really need to try to reduce the number of simulations that you have to do for the accelerated propagation. You have high-dimensional output over the whole region, perhaps with conflicting characteristics. You have a correlated high-dimensional input. And generally, this high dimensionality creates significant burdens on the memory requirements that you need to do the accelerated propagation. When you try to use some of these state-of-the-art approximate techniques like surrogate models or low-fidelity models, which they're challenging on their own, now they become even more challenging because you need to capture the aleatoric variability. You have missing data. Probabilistic characterization is important as you talk about UQ. And scalability of algorithms is tough. Many times when we talk about high-dimensional inputs and outputs, we think like maybe tens, maybe hundreds. The problem is these regional problems, high dimensionality can easily exceed millions. So how you're going to scale your algorithm to this high level becomes really critical. Okay, that was sort of the motivation of the whole roundtable discussion. I will move. And now I should point out, each of the talks that you're going to hear today, we're going to address different parts of the challenges. In my talk, I will specifically in these 2 red boxes. So with that, let me start with my timer, and we'll start with my talk, which is going to be on adaptive Monte Carlo algorithms in this setting. And I will try to put the discussion in a context of a specific application. So we're going to look at some of my work that my group at the University of Notre Dame has done with NOAA on real-time search forecasting. So before a hurricane makes landfall, this could be a few days before we have landfall. This is the advisories that you typically get. So some nominal path and some cone of uncertainty. And really our task is to propagate this information to estimate the expected search statistics so that we can manage evacuation decisions. So this is the nominal advisory, and you have some traditional forecast errors, which create your probabilistic distribution, and then you create a storm of storm scenarios, an ensemble of storm scenarios to quantify this uncertainty. Then you adopt a computationally expensive numerical model that using this parametric input can predict the surge over the whole domain. This could be slosh or Radsirk, but no matter what, each simulation is going to take many CPU hours, thousands of CPU hours. And then predicting the storm for each of, predicting the surge for each of the storms, you can get the statistics of interest through the whole ensemble. So one of the unique challenges here is that you have in this whole domain, you have a very large number of locations, up to a few millions that you need to estimate the risk for. So in the UQ context, these are your quantity of interests, your Q of I's. And this process is repeated. So generally every 6 hours, you have a new storm advisory, and then you're going to repeat this whole thing. And our challenge here is the computational, expensive model. So what we really are trying to do, we try to really reduce the number of simulations that we have to do in a Monte Carlo setting. There are some very standard techniques that you can adopt to get this adaptivity. And the unique, thing in the context of real-time search forecasting is sort of you can apply this adaptivity at no additional computational cost, because you have done your estimation for the case advisory. So you have a lot of information, and while you're waiting for the next advisory, the K+1, you can tune the adaptive characteristics of your algorithm, and then you are ready to apply it at the next iteration. So really, the adaptivity is not the big challenge here, especially since the computational burden is minimal. You're already going to use information computational simulations that you already have performed. I'm going to specifically talk about this first, the top two variance reduction methods, importance sampling and multi-fidelity Monte Carlo. And I will focus a lot on the challenges that are created by this very high dimensional output. So in adaptive importance sampling, okay, so if you want to think about it in the context of mathematics, that's really the problem that you are trying to estimate. P of X is your probability distribution from the forecast errors. HI is your consequence measure. And this is how your estimation would look if you do Monte Carlo or importance sampling. And really what you try to do, you try to reduce, by introducing this importance sampling densities, you try to reduce the number of simulations, capital N, that you need in order to have high accuracy. And we all know the importance sampling density is proportional to this integrand. Maybe you can think, well, this requires some computational cost in order to approximate it. But again, the trick is that, hey, you can use information from past advisories to adaptively establish this with very small additional computational burden. So a lot of details are in this paper that are referencing here and at the top. Our problem here is this. Each quantity of interest, so in other words, each location within this domain will have a different optimal importance sampling density. And here I'm plotting what is the mean of the optimal density for the storm size, and you can do for the other type of uncertainties that you have, cross-track variability, forward speed, or storm intensity. So, and this is in the Gaussian space, so your prior mean was 0, and you see across the domain, you have really big variability. Each node wants a different importance sampling density. So you have really conflicting, competing objectives that you need to address, because at the end of the day, you cannot assign a different importance sampling density to its nodal location. Similar, when you talk about adaptive multi-fidelity Monte Carlo, we're going to have a similar problems. So how you do here multi-fidelity Monte Carlo, you assemble all the information from the past advisories, and then you can develop a low-fidelity surrogate model while you're waiting for the next advisory. So when the next advisory comes, you're not only going to use the computational expensive model, but you can also come and use the low-fidelity approximation in order to get your final statistics. So mathematically, this is how the problem works. The key optimal decision here is how many high fidelity and low fidelity simulations you're going to do, how you're going to allocate your budget in these two models, or equivalent, what is the optimal budget allocation. You can go and calculate what's the optimal budget allocation that minimizes the variance. And again, our challenge here is that this is a function of the quantity of interest. So again, this whole domain, its different location will prioritize a different optimal decision, primarily because the optimal decisions are related to the correlation between the high and the low fidelity model, which is different within the whole domain. So mathematically, that's our problem. We have this adaptive, a Monte Carlo algorithm, which we can apply relatively easy because we are leveraging information that we already have. But our problem is that each of these algorithms have some optimal decision. And we need to establish a common selection across all Q of I's. And so the compromise solution is just going to be a weighted average for what's the optimal decision for each of those locations. You can select your weights. Typically, we use the variance because that is reflective of the Monte Carlo variability. Again, a lot of these details in these two publications. So the other question is how to efficiently establish this. So if I have 1 million in outputs, okay, I need to do this compromise solution. Do I need to carry all of them? And generally the answer when you have high dimensional output is probably it's very going to be correlating these type of problems. So the solution is you use some latent variable projection. So you can start with 1 million points and you project using the whatever projection into latent space method that you want. This could be tens, maybe to a 50, so significant reduction. And then you perform your UQ task in the latent space. So in this case, we're going to make decisions for adaptive UQ algorithms in this small dimensional latent space. And of course, if you need to do some other UQ task, you might need to project back into the original space. But the trick here is that the computational intensive UQ tasks are performed within the latent space. There are multiple, projection, latent variable projection algorithms that you can use. This is a number of papers that other people have actually done excellent work. This is a couple of papers from my group on this specific problem, the coastal risk assessment. And they're going to give you, again, this projection is going to give you some unique benefits. In the context of what we're discussing here, really this red box is what we're leveraging. You actually get some memory savings, and because the multi-fidelity Monte Carlo requires surrogate model, we have some additional computational efficiency in the surrogate model calibration. So really quickly, let's go back and figure out the challenge of the high dimensional output. So I'm going to use the speed up to assess the performance improvements that I'm getting. So the speed up is going to be the computational time of the Monte Carlo versus the adaptive Monte Carlo. Equivalent to this is the improvement statistical accuracy. So in other words, a speed up of 5 means that you can get the same statistical accuracy 5 times faster, or for the same time, you can have 5 times better statistical accuracy. And I'm going to compare these two versions. The idealized implementation, which is the best, the idealized efficiency. So if I could make independent decisions for each of my QOI, what would the results be? Of course, this is impractical, so we're going to come and compare that to the practical implementation. What is the actually achievable efficiency when you need to establish this compromise solution across your multiple outputs? I'm going to do this for different statistics and for the different storms. A lot of the details are in this paper referenced down here. So I'm going to compare adaptive importance sampling and adaptive multi-fidelity Monte Carlo, and on the top you're going to be coming and seeing the idealized implementation, at the bottom the practical implementation. So this is the variation of the speed up for the mean surge, the 10% exceedance probability surge, and the 1% exceedance probability surge within the domain. As you can see, the more rare the event, the better the importance sampling density, the bigger the benefits of the adaptive importance sampling density we expected, and then the lower benefits of the adaptive multi-fidelity Monte Carlo. This happens because the correlation for these more rare events between your low and your high fidelity model reduces. So if we had seen this, okay, this advanced implementation, evidently we would all be promoting the adaptive importance sampling. That's, for most of us that work on UQ, that's the first tool that we always think of. Yeah, that's what we're going to come and use. The problem is that this is the idealized. I can make independent solution, which is impractical. So if I do the compromise solution, this is what I'm getting. And I would like to point first here that I'm using the scale for the practical speedup is very different. So if I was using the same scale between idealized and practical, this is how it would look like. So when you're forced to establish this compromise solution, the efficiency of your adaptive importance sampling is greatly reduced. It's not zero, you have some small efficiency as you can come, sorry, my bad. So you have some small efficiency as you can come here, but it drops to lower even the adaptive multi-fidelity Monte Carlo. So these are results for Superstorm Sandy. We have exactly the same behavior for Hurricane Irene. Yeah, this is I'm going to have the same resolution of the, in the idealized and practical implementation. And, if you say, here, this is for North Atlantic, what's happening in the Gulf, this is for Hurricane Gustav, exactly the same result. So these are my final slides. This is my summary. These are some of the challenges that I discussed that they exist in the UQ setting. And my main key points that I wanted to discuss is, look, in this world where you have a very large number of QOIs, your adaptive Monte Carlo starts losing efficiency because you need to establish a compromise solution, something that many of us typically forget. We think that whatever we did on the sort of individual building is going to work on the region. And generally, the more aggressive your algorithm is, so in other words, the more it tries to extract information to improve computational efficiency, the more it's going to lose when you try to establish this compromise solution. We saw it. Adaptive importance sampling is a really aggressive, adaptive algorithm. But at the moment we're at state, I need to establish the compromise solution, we greatly lost efficiency. And with that, that's the conclusion of my talk. Feel free to post questions on the Q&A, and then I'm going to pass the torch to the next speaker, who's going to be Paolo Bocchini.
You can all see my screen. I want to start by thanking Dr. Taflanidis and SimCenter for inviting me to participate in this panel. I'm very excited to be here, and I will talk to you about uncertainty quantification as a mechanism to drive multi-hazard scenario selection. I want to start by using the framework that Alex presented before. All of these risk attributes and specific challenges of regional hazard quantization are common foes for me and for many of us. We had the pleasure of dealing with all of these, I guess. But today, I want to focus in particular on those related with the hazard exposure, and in particular, the need to well capture the correlation among spatial location when dealing with the hazard and the aleatoric variability of the hazard that then, of course, is propagated throughout the analysis until the quantities of interest. If we look at the challenges in particular, the one that I'm going to focus on is the need of computational efficiency achieved through a drastic reduction of the number of simulations that are needed to estimate our results. So in summary, I will talk about, in the context of hazard exposure, about the way to capture correlation among spatial correlations and represent correctly the aleatoric hazard variability, and how to do so with the smallest possible number of samples. So how do we deal with the hazard maps? This may not be the case for today's audience, but it's common for me that when I talk about the need of and challenges in capturing a regional hazard, some people respond, well, but we have hazard maps, right? They give us the hazard and they're presented in the form of a map, so they're good for a region. Unfortunately, that's not the answer. Hazard maps are a great tool. Here, there are a couple of examples of those developed by USGS for earthquakes, but we know that we have access to similar maps for all types of perils. But hazard maps are developed for studies on a specific site. They give us the hazard at a single site, whereas when we're dealing with a region, be it to study a whole portfolio or something like a networked system, like a transportation network, a power transmission network, what we want to study is not only the probability of having a certain intensity, let's say a certain level of ground shaking at location A, where my first bridge is positioned, and also having some information on the probability of having the various levels of intensity measure at location B. We also want to know the probability of having that level of ground shaking simultaneously at both locations. And if we're dealing with a network with hundreds of locations, as Dr. Taflanidis was saying in the previous presentation, we may want to know that probability simultaneously for all possible combinations of intensity at all locations. And this is commonly done through simulation by selecting a number of scenarios, realistic or artificial, that have the ability to capture the overall variability of the hazard that can impact a region, while also carrying the correlation among the level of intensity at the various locations that we want to represent. One possible way to select scenarios that will be able to capture this variability is what we call hazard quantization. The basic idea is the following. You can imagine all the possible events that can impact a certain region as dots in a space like this, with some characteristics towards the middle that are a little bit more likely to occur, and some fringe events around the boundary that are a little bit less likely. In theory, we would want to study all of those events, but more realistically, we'll be able to select and analyze only a small subset of those events. But even just by looking at it, we see that this small subgroup is not really representative of all the variability that we see in the first picture. So a first step to make things better is to try to understand what area each one of those scenarios can represent, and use that as a sort of probabilistic weight. But even better, we can try to use those areas to space more evenly the scenarios that we study and make sure that they cover more densely the more likely regions, but also investigate what happens at the fringes. Now, this is just a pictorial representation in a two-dimensional Euclidean space. We will have to do this with a highly dimensional or even infinite dimensional case of scenarios affecting a region. I also have to mention that what I will talk about is not the only possible approach. There are many others. K-means clustering developed by Stanford University, Jack Baker's group and his collaborator. Optimization-based probabilistic scenario selection at University of Delaware, Dr. Davidson and her collaborators. At UIUC, Paolo Gardoni and his team have been working on closed-form analytical alternatives to capture these variabilities, and I'm omitting many others that are valid and popular, but I want to talk about this one in particular that we have been working on for about a decade. Over these years, we applied this technique to various types of perils. We started with earthquakes, then hurricanes. We worked also towards ecological hazards like epidemics. We tested the methodology also on other types of problems like stochastic mechanics, life cycle functions, ground motion time mysteries, and more. And we developed some variations of it, like one that we call hybrid quantization to mix synthetic and historical hazard scenarios, multi-step hazard quantization that allows us to have differential accuracy on different portions of the domain that we study. But the general story is that the techniques in general works pretty well. These are just two examples of what can be achieved with this technique. In this case, the quantity of interest is the autocorrelation among different sites. So here we fixed a pair of locations, and we were looking at the autocorrelation for our field, be it the hazard, wind velocity, ground shaking, or whatever it is. And we're trying to capture the variability in that estimate of the autocorrelation. So in other words, the variance of the estimate on our quantity of interest. And you see that if we use this technique, even with just 50 samples, we have the type of spread, the type of variability that is similar to what we would get with 10,000 samples with purely random simulation. And this plot represents a similar concept. You see how the stochastic error on the autocorrelation goes down as we increase the number of samples that we use. But when we use the technique that we just proposed, functional quantization or hazard quantization, that stochastic error is a lot lower. And here the vertical axis is logarithmic. So being down here means a very substantial reduction. So we can get with 50 or 100 samples an error that is lower than we would get with 10,000 simulations otherwise, right? So this again goes in the direction of trying to reduce the computational burden by reducing the number of samples that we study. Now, more recently, we started pushing a little bit the envelope to study problems where we need more than one intensity measure to describe the hazard in the region. For example, if you're studying earthquakes, you may have to deal with a collection of buildings that combine short buildings susceptible particularly to short period accelerations, tall buildings that are more susceptible to long period frequencies, and buildings in between. And also in this case, we developed a new version of the methodology that can give us global assessments like the expected global loss with very good accuracy. Now, the problem, though, that this technique faces all the times, but especially when we deal with the multivariate case, is the fact that we have a systematic underestimation of the variance. Now, this is a relatively small issue in most applications, but it becomes more severe for multi-hazard quantization. We underestimate the variance, we overestimate the correlation coefficients, especially for the multivariate case. Now, here you see an example where the blue curve, that is our hazard quantization result, is a little bit steeper than the black reference, that is the ideal solution. Now, the good news is that we are able to identify that error in our estimate as the procedure moves. And in some cases, we also developed closed form solutions that can predict that error upfront. And the main point of this presentation is that we can use our assessment. So we can use our uncertainty quantification to basically drive the selection of scenarios for the process and correct this mistake that we know we would be doing otherwise. An example application of this technique is to the case of hurricanes that generate both wind and storm surge, two intensity measures that are very different from each other. This is the algorithm that you can find in a paper that is already available online. But the important thing is the results. You see that with traditional hazard quantization, we have several locations where the error is quite large, and you see these purple dots. Whereas if we use this hazard quantization with UQ, you see that the error is very low pretty much everywhere. And if we look at the reduction of the error, you see that at several locations, this reduction can reach 60%. So, conclusion. I think that when Dr. Taflanidis asked me to give this presentation, he was expecting me to show how regional scenario selection can be beneficial to uncertainty quantification. But I pitched to him something that was doing a little bit of the opposite and show how uncertainty quantification can be used for a better scenario selection. But of course, if we do a good scenario selection, then we can address the problem of capturing correlation among the various locations and the aleatoric hazard variability, which in turn allows us to use a very small number of scenarios and reduce our computational complexity for the uncertainty quantification of the ultimate variables of interest that you want to do. So I want to acknowledge and recognize all the contributors to this line of research, several of my current and former students, and some collaborators at Lehigh and now at other institutions, and thank everybody for your attention.
Thank you, Paolo, for the excellent presentation. We'll pass the torch now to Jamie.
All right. Are you seeing my presentation?
No, we still see the notes page, Jamie.
Let me swap settings. All right. Doing good. Well, thanks so much for passing it to me, Paolo and Alex, for the invitation to join this group. It's a really nice group of colleagues and friends, and I was kind of honored to be a part of this conversation today. If we take a look at the title of the topic here today, it clues you in on which pieces of the puzzle that Alex was referring to. We're looking at some of the issues of fragility analysis for structural portfolios and seeing how we might leverage surrogate modeling in the construction of these vulnerability models, but also how that fragility fidelity interacts with some of the other choices that we make along that whole pipeline to risk and resilience estimation in this regional setting. I do want to acknowledge some of our group members whose work I'm representing today. I think we have on the line Raul Rincon, and Janish Patel, whose work I'm going to highlight in the talk. So hopefully they'll join us in the discussion later. Back to those overview slides. In some shape or form, I'm going to touch on this idea of missing data, but you'll see that we focus on that more from the perspective of kind of our knowledge of the system and also some of our choices and how we model them, and mostly look at leveraging surrogates for computational efficiency along that fragility and risk and resilience pipeline. So when we look at this challenge of portfolios or of hundreds or thousands of structures, one concept that we've been promoting for a number of years is this idea of parameterized fragility models as a bit of a compromise between leveraging the classic archetype fragility function, which often is using maybe one representative structure for a whole class, and leveraging fragility functions for that class for each in the sub-portfolio. Or the other extreme, where we might derive unique fragility functions for each structure within our regional portfolio. And I'll acknowledge that I think that could potentially be within reach, even leveraging some of the methods that we're talking about here today. But we've proposed this idea of parameterized fragilities as a pretty transparent or portable model that could be leveraged by other researchers, but allow us to support some of the UQ efforts in a regional risk and resilience estimation, where we condition our failure probability on a vector of intensity measures. These may be some like Paolo just showed us with joint surge and wind or wave characteristics, as well as a vector X that may be those that we either know, perhaps from an inventory, or unknown random variables that we want to propagate through our analyses. But in service of deriving those parameterized fragility functions, we need to cover a whole range of a parameter space, not only on the intensity measures, but also structural characteristics. For example, for these tanks, we might be looking at different diameters or shell wall thicknesses, material properties, and so forth. And our goal is our limit state function estimation. So in the case of tanks, we may be looking at shell wall buckling, for example, or uplift and overturning of tanks. Herein lies one opportunity to leverage surrogate models for more efficient, complex load modeling for use in that fragility derivation. So for example, those computational fluid dynamic simulations of the hydrodynamic loads, the surge and wave and fluid flow on our structural walls, we may leverage a statistical surrogate to approximate what we realize from, say, our CFD analysis. And this is just one illustration in some past work, leveraging an artificial neural network for estimating pressure on our tanks in order to efficiently derive some of those parameterized fragilities, either with numerical simulations or analytical approaches. But herein lie other opportunities beyond the surrogates themselves for efficiency. We may want to leverage other techniques along the way, such as dimensionality reduction techniques or efficient sampling strategies. So in the center, you see an example of the pressures estimated around that tank. We might look at, since we want to estimate them at each point along the structure, leveraging things like principal component analyses to reduce that space. Or look at how we might have improved sampling efficiency, leveraging approaches like active learning for guiding that next sample as we're estimating either our pressure or our failure probability with in a particular confidence interval. So in this case, steering our sample generation in order to achieve that target confidence until our stopping criteria is met. But it's not only in the load modeling portion of our fragility work that we might leverage these. For a decade or more, we've seen people leverage surrogate models within demand analyses on structures, whether it be for individual structures, but surely for portfolios of structures where we're covering a whole range of a parameter space. For example, you see here work over a decade ago looking at different types of meta models, often inspired by machine learning algorithms for estimating the responses of bridge components under seismic excitation, things like our abutment deformations, our column response, our bearing displacements, etc. But a lot of times that work was done in the context of what we've referred to as univariate surrogate models, meaning developing an individual statistical approximator for each component response within that structural system. I would say in recent years, we've seen more of a shift towards these multivariate surrogate models that allow us to represent with one single model the response of multiple components such as bearings, abutments, columns simultaneously, but also to preserve that correlation structure and respect the covariance, the residual covariance and those regression estimates. And you see two different examples of some past work that have taken this approach of correlated model residuals through either multi-output Gaussian process regression models, some work by Al Du on the left, who's at UT San Antonio now, and some work on the right by Pedro Bendini, who's now at University of Sherbrooke, leveraging Gaussian mixture models. So we look at clustering as we inform our joint probabilistic seismic demand models. All of this is really in service of efficiently estimating those joint responses of our components as a part of fragility estimation, especially when we're covering this huge sample space in a portfolio of structures, but respecting things like correlated component responses and errors. The goal of a lot of these is to leverage them in, for example, those parameterized fragility estimation. But even with the best surrogate in hand, there are other input parameters to these models, which in and of themselves may be uncertain. For example, we may have different levels of knowledge on our inventory, for example, our number of spans or our column height, or on those uncertain random variables tied to, say, material properties. And so I think this form of model, albeit we need to complement it in a numerical integration or a Monte Carlo approximation, can allow us to then propagate some of those other sources of uncertainty. Here's an example of looking at fragility models with different levels of knowledge. So we've broken down that input parameter space X into those that we know, XL. On the left, we see that we're considering them all to be uncertain random variables. And as we move to the right, we have more knowledge about our system. So looking at how that influences our uncertainty about our fragility estimate. But that, of course, is a piece of a broader risk or resilience estimation. And we can explore how that influences other types of risk metrics. For example, here we look at portfolio level losses. So across our whole portfolio of structures, how that knowledge or refinement in our fragility models propagates to influence our expected total losses in the portfolio. We see that not only may we have uncertainty reduction in our loss estimation with that additional fragility content, but we may have a shift in our estimate as well. Or we can explore not only at the scenario level, but how that may be potentially influenced or even overshadowed as we propagate other information, for example, on the bottom across the whole range of different magnitudes of events. But this really is just one of many questions that we're exploring as a part of a risk and resilience pipeline. Fragility, fidelity may be one, but perhaps we're also having to make decisions on our network resolution. So thinking about some of our discussion upcoming and some of the work Abdullah is showing, wanted to quickly highlight an example of where we've explored this coupling between fragility, fidelity, and model resolution and a seismic risk estimation of a transportation network. And the real takeaway message here is that even as we refine our fragility estimates and leverage them for uncertainty, quantification, and propagation, we may have model choices that overshadow some of that refined fragility estimation. So on the top, we see with that propagation of uncertainty in our input parameters, we see the reduction in errors about our total loss estimate, but that may be overshadowed when we get to the regional scale or global metrics as we look at the resilience quantification at the bottom. Just a few quick takeaways. Certainly, I think we see a lot of benefits of efficient surrogates for multi-response systems and UQ enabled across scales. But there are other modeling choices that may interact with this strategy. And also want to suggest the opportunities that we have to kind of pave the path towards these types of studies with open data and model sharing. So that I'll pass it back to you, Alex, and to Abdullah.
Thanks, Jamie, for the excellent presentation. And Abdullah, the floor is yours for the final presentation of the roundtable.
Can you see my slides?
Yep.
Thank you, Alex and SimCenter, for this opportunity, and good day to everyone. And it's a great pleasure to be here virtually. I feel I was a little overambitious when I was preparing materials for this. I see how much I can cover today. As nicely explained by my colleagues earlier, we can argue that UQ is an integral part of all elements of resilience analytics. And here I focus mostly on the systems and decision making. And we can see this as a few examples for this more complex and broad problem. So let's imagine a network, for example, a power system, and we would like to see how this network performs under uncertain hazard conditions. We can generally present the operation of many networks, such as power grid, as optimal power network flow problem. And we see here the constraint optimization model, where phi of theta is basically the cost function, and the constraints are conservation of flow and link capacity. We can then perform AC power flow and also optimal AC power flow analysis using multiple packages, including Mat Power. And we can have also these models to capture cascading failure. During natural hazards, however, some of the nodes and edges may fail, and the question is how the failure probability of the system changes under those conditions. And we then can, to assess the performance of the system, we can set a limited state function at the system level. And given that the possible scenario space is extremely large and each simulation can take time depending on the scale and nonlinearity of the problem, then we are looking for efficient ways to analyze network reliability. So in this particular work, we developed an adaptive reliability analysis method for such problems. And this directly builds on the adaptive methods for components and smaller systems. So the general idea is that we adaptively train a surrogate model that progressively learns about the limited state. And we selected BART, Bayesian additive regression trees, for this purpose because it has a robust predictive performance for relatively high dimensional, medium to high dimensional problems of a few hundred dimensions at least. And it can handle binary variables as input also. And also it can provide estimates of uncertainty around its estimated responses. Since we are dealing with a high-dimensional problem, the initial training set, the size of it becomes important, and we established a process here. And also, we defined a learning function that helps us to find the best next training points for training the surrogate model. And this is a modification of the well-known U-learning function, except that in the denominator, instead of sigma that is normally used, we are using the credible interval that is provided by Bayesian additive regression tree. And we then developed a stopping criterion for training based on the expected value of the new training batch for the improving understanding of the limited state function. And using all of these, then we established a iterative process for adaptive reliability analysis. Here, I briefly present the results. In the x-axis, we see the limited state function, g hat of x, as estimated by BART. To the left of it means that we have candidate points estimated as failure. And in the y-axis, we see the uncertainty around those estimates in the form of credible interval. And we see that as the training continues from 0 to 20 to 180, in this particular case, the adaptively trained surrogate model identifies more of the candidate points as failure. We also see that initially the model is underestimating its uncertainty around those estimates. And as the training increases, the uncertainty estimation improves. Actually, the uncertainty increases. And after further training, the uncertainty starts decreasing. The bottom left shows the convergence of the failure probability estimation by the adaptive method to what we derive from Monte Carlo simulation. And finally, in the bottom right, we see the relative error of 3 methods, including a deep neural network, and also a passive BART, and as well as active BART, where we see active BART is performing better, converging faster. And we apply this to more complex, larger scale problems. And we see in all cases that the adaptive method is converging faster. And the other observation is that as the complexity increases, the benefits of using adaptive methods become more evident. What I showed earlier so far is what we call simulation-based methods, meaning that we train a machine learning model based on labeled data that is produced by physics simulations. And an alternative and emerging method is to directly solve the partial differential equations underlying the physics of flow in these systems using machine learning models. And an important variant of it is physics-informed neural network, or in short, we call it PIN. Here, I very briefly present our PIN development for the transient mixed flow of gas in transmission pipelines, and we see the schematic configuration of the network here. The partial differential equations governing the flow is shown here. These are highly nonlinear equations and are difficult to solve even using conventional methods. In PIN, we generate a set of points, we call them correlation points in a space and time, and then we find the outputs as the hidden solution of the PDE, here in this case, pressure and mass flow. And using outer differentiation, then we are able to find the derivatives at those points, which align with the actual values that we estimated, goes into the left-hand side of the PDE, and is one of the loss terms along with the violations of the initial condition and boundary conditions, then it forms a total loss. The problem becomes more challenging when we want to go from one pipe to a network of pipes, because these PDEs will interact. And the learning task becomes more significantly challenging. And here we develop this nested structure where the initial and boundary conditions are hard-coded into PDE, and that reduce the number of learning tasks and made possible to solve the problem using PIN. So here are the results. We see that the PIN model is able to provide good agreement with the state-of-the-art conventional methods. The main benefits of it is that when we develop a parameterized PIN model, then we are able to perform sensitivity studies quite fast, and also Here we see with respect to friction factor and diameter of the pipe, and also we can propagate uncertainties quite fast. We generated 50,000 samples of temperature, and then we were able to find the distribution of the maximum pressure across the network quite fast. We can extend these even one step further and try to leverage the architecture of the network more directly through graph neural networks. And in a prior work, we developed a graph attention-based model for flow analysis in power systems. At a high level, we use the violation of the Kirchhoff's law as the loss in the training process. And here we see the model updates, and it reflects the impact of the learned physics on the flow responses, as we see here. And also in the bottom, we see the attention mechanism that the model has learned from the network. The model reached high accuracy relative to Newton-Raphson method, which is the basically benchmark solution. And the errors were in the range of 10 to the power minus 2 to 10 to the power minus 3%, while the simulation speed has increased by 2 to 3 orders of magnitude. So this allows kind of extensive uncertainty quantification studies quite rapidly. The last example I'd like to cover is about the UQ in optimization for decision making, and we'll see this briefly for application resilience of smart power systems. For a smart power system, I mean systems that have reconfigurable switches, and therefore the system can reconfigure in real time or near real time. And also it has distributed generation units where it allows the system to form microgrids in the system. Here is a framework that we came up with for these smart systems. At the center, we see the stages of system response to a shock, and wrapped around it, we see the visualization of the optimization model. And at the bottom, we see the formulation of the stochastic, multi-stage stochastic robust optimization model we developed for this. The first stage is for pre-event hardening, as you see here. And the second stage is about the direct shock of the hurricane and the impact on the system. And the third stage is about the self-healing capabilities of the system. And the fourth stage is for the recovery of the system. So because of the time, I'm going to focus only on the second stage. We characterize and propagate uncertainties in all the stages of this model, but particularly I'll focus on the second stage. We cast that problem as a stochastic robust approach, and the outer level is a maximization problem. And given an uncertainty set that we see here, we designed the outer problem to find the lines whose failure causes the maximum damage to the system. And this formulation of uncertainty setting is inspired by entropy. One of the contributions of this work is that with the setting that we see here, we are able to capture the effects of stochastic weather-related variables on the shape of the uncertainty set for the line damages. So basically, the uncertainty in one stage of the solution defines the shape of the uncertainty in other stages of the solution through a robust optimization model. And in the inner level, we have a minimization problem of the cost of induced damages by optimizing power flow variables, but all in a solution space that satisfies the physics of power flow. The last slide, I briefly talk about the results for the IEEE 118 bus system. This is a more complex version of the test bed because we made it smart. We added DG and controllable switches. On the left plot, we see the system performance with and without hardening in blue lines, and we see that applying hardening in a smart system can considering the operation of a smart system can improve the resilience of the system. But also on the red, we see the incurred costs that not only we are improving the resilience, but also we are reducing the cost of operating the system for utilities. And that's an important consideration, especially in power system, because the incurred costs to utilities, if we don't pay attention to in our processes, will be transferred to consumers of electricity, and that may affect the affordability of the electricity in the long run. Thank you for your attention, and I'd like to thank NSF, DOE, and other organizations who supported this research.
So we have reminder, as Matt said, that if you have any questions directly for the speakers, not for the broader discussions, you can post them on the QA. We will not move. Again, if you have questions, please post them in the QA directly for the speakers. We'll have a couple of questions. So I guess, Paolo, this is for you. So I guess I'll try to simplify the question. So on what information are you using for the hazard quantization? So do you have some output results that you leverage to select the scenarios, or that's purely done on the input without seeing any output?
Great question. The versions that have been published so far are only trying to capture as well as we can the input, right? We have some proofs of optimality on our ability to capture the input. However, as you suggest, as the question suggests, it's actually a good idea to compromise our optimality on the input to improve our ability to represent the output, which is what we care most about. And there is a student who I think is here, Sena Mursel, is precisely working on how we can embed some of our information on the filter between input and output to drive our selection of the input samples.
Another question. So again, Paul, I think that sort of also pertains to you. The question is, have you, and we're going to move it a little bit in the question of biases. So I think like in some of your results, you saw efficiency, like accuracy in terms of correlation. The question is, do you still have similar improvements in terms of bias?
Yeah, that's the easy part. The hazard itself, our ability to capture the hazard curve is very, very good, and you can reduce a lot the number of samples if you're only looking at capturing the hazard curve. The capturing the correlation is a little bit more difficult, and that's why I was showing those results.
Yeah, we'll pivot to another question that again related to bias, and I think this pertains to all of us. So I will take a first crack, and then I'll let other people chime in, even though Paulo sort of addressed it from his perspective. So the question is related to the eternal conflict between faster computations, computational efficiency, versus bias. What bias comes in your estimation? So how do you balance between these two in a broader sense? So I'll take the first crack. In the algorithmic, when you talk about Monte Carlo, you're always going to be unbiased. So either you do adaptive importance sampling or adaptive, multi-fidelity Monte Carlo. There is really no approximation. You're going to be unbiased, not asymptotically unbiased. You're going to be unbiased. So what we are looking at that computational efficiency. In other words, what is the best decision that's going to give you the best reduction in terms of statistical terms? But the methods itself are unbiased, and that has to do with any Monte Carlo algorithm. Unless you make some mistakes, you're going to be unbiased. Now, when you do have some approximations like a surrogate model, a reduced order model, like you're going to come and introduce some bias. The multi-fidelity Monte Carlo removes that bias by combining the high and the low fidelity. So that's from the perspective of the algorithms. And then I'll let each of my colleagues try to address these questions of how do you, what's the smart approach based on your opinion on the things that you discussed, not in the broader sense, to handle these internal conflicts. I want unbiased predictions and I want greater computational efficiency. Paolo, we can start with you.
Well, so first of all, I want to say that here the conversation becomes more complex to have in this form. At least for my case, there is the bias in the sense of the first order statistics, like the marginal hazard. But there is also the bias in the sense of whatever quantity of interest we discuss, you can have the bias in the estimation and the variability in the estimation. So for our case, for example, we have an excellent approximation of the first order statistics, bias and variability. We have a good approximation of the second order statistics in terms of variability. The issue that I was showing was bias in the second order statistics. And in that case, we did find a way to account and sort of renormalize for that bias through analytical methods upfront. So I think that there are a lot of problems where we don't even dare to try to get a sort of preliminary approximation of that bias. It may not be perfect, it may be under some conditions, but it could be enough to give us the ability to correct for that bias, even if we don't have the perfect analysis. So this is something that we tried, it worked, and I suspect would apply to a lot of the problems that we study, and even if we don't, it's not the first direction that we go into.
Anyone else, Jamie or Abdullah?
I can maybe add a little bit also. From the adaptive reliability analysis perspective, I could say the use of the surrogate model is primarily to understand the shape of the limited state function. So we are, and once that is established, then we normally go through sampling methods to do the reliability analysis to find the failure probability. So the bias then there could be in how the surrogate model is identifying that limited state function. And one approach that I believe can help is many methods have been focusing on the accuracy of the surrogate model around the estimation of the shape of the limited state, but we can go one step further and set the objective to what is the how the surrogate model is performing or being trained for the accuracy in probability of failure estimation directly. So rather than on just the limited state, and that's to a good degree would resolve some of the issues. And there are ways to find analytical bounds and kind of that would inform the model, the training, the adaptive training process to better select the training points around that region.
Let's see, I'm trying to look at, okay, so one more question that we got. Is it feasible to develop state-dependent fragility functions for multi-hazard scenarios? I don't know if anyone is interested in taking, I think like someone that talk about multi-hazard or fragility.
I guess I'll comment briefly. You know, I kind of sped through some of the examples here, but one of the concepts of the parameterized fragilities is that ability to capture. We could look at multiple states from the state dependent, but I think the multi-hazard emphasis is what motivates that in part beyond the portfolio application efficiency, but that vector of intensity measures that may represent joint IMs. And then we have to take care in looking at that issue of spatial and temporal correlation in those hazard intensity measures as well. And that I think also suggests to us that there may be a broader not single event temporal correlation, but looking at multiple events even throughout the lifetime or life cycle. So I think that multi-hazard word maybe is loaded. The example that I showed suggests that it was from a single event, like a joint wind surge wave from a hurricane, but I think it also paves a path to looking at multi-hazards that may have longer temporal lags as well.
Thanks, Jamie. I think one other interesting question, I think it's an extension point of discussion, but I would like to address it, is related to the broader epistemic uncertainties in these problems. So in other words, you have such high variability in a lot of the information that come in to put these regional risk assessments. And here we're talking about sort of the efficient propagation, so how those two balance. That's an excellent question, and that's a really tricky question. And that comes into one of the challenges that I was talking about, information fidelity, and it's really critical because it also depends on really what you are interested in calculating. So what is your final decision variable? If it's just the performance on the average in the whole domain, then perhaps the epistemic uncertainty becomes a little bit less relevant, even though it's important. But I think there is still a lot of work that we should do in the UQ context of what is the relevance of your information. I call this information fidelity. So how are you going to create the assets, and not only what is the type of model that this asset is going to have, because there is a lot of uncertainty that comes from the model, but also what information comes and is used to develop these models. And evidently, you're going to balance from the really important, assets. You're going to have more detailed models with, perhaps better quality information, and the less important assets, you perhaps some approximate model with more average information across the region.
Yeah, I think one piece of that we didn't really get into in detail, and maybe also Raul Rincon might join some of our discussion when we open it up to the audience. But that kind of prompted us to try to look at this systematic kind of layering of model choices throughout that resilience pipeline, that we could put all of our effort for a decade into these refined high fidelity parameterized fragility models, but then there may be other model decisions or information that feed into those that either overshadow or wash out some of that. And it's really more of a fit for purpose. If we're going for this particular global performance index, then perhaps we would suggest this particular chain of models. Whereas if we're going for another prioritization, maybe tailored to each structure in that portfolio, we might see the benefits of some of those high fidelity models. I think we struggle with comparative methods. I mean, we've been using just some systematic combinations of different models and statistical distance measures. It's a little different than our classic global sensitivity analyses when we're starting to get into some of these model choices. And so I think that could be an interesting open discussion, is how we tackle some of those.
Okay. I'll pose one more question to the group, and then we're going to stop the recording so we can follow up with a discussion. I think that's a key question that comes from the SimCenter perspective, and I think it pertains to all four of us. A comment of how the work of the SimCenter moving forward, especially, can help promote sharing, these ideas, models, approaches that were discussed. I'll take I'll just give a 30-second perspective from my own point of view. There's this, UQ challenges that we face when we move into the regional assessment. And I think coming and creating a playground where different models can be integrated to tackle these larger problems, because a lot of us working on UQ algorithms or UQ approaches develop from a specific perspective, and we don't necessarily have the ability to apply it in the regional scale. So having the ability to plug and test these algorithms in a regional risk assessment, to promote a regional risk assessment, that is one of the things that the SimCenter can help. But I'll leave to the next of my colleagues to offer their points of view.
I will just add that I agree with Alex, and I've seen a strong shift in the SimCenter's activities over the last couple of years, maybe. It took some time to reach the level where they could open up their models to the community, really, right? It takes time first. You have to reach a minimum level of operability internally. But I think now SimCenter has reached that level, and the models and the personnel are open to our contributions, and we had discussions. The bandwidth is always limited, so it's difficult to do everything, but I think that it's a good opportunity for the entire community to think about the SimCenter as a partner and a destination for our codes.
And I like your comment, Alex, about this idea of having a playground for kind of plug and play testing influence of different models within that pipeline. Most likely researchers are focused on an individual portion of it, but then overlaying it with some of the tools, whether it be, I think some of the current emphases on UQ tools across our hazard, damage, consequence, but as that consequence portfolio grows in our minds, and as the hazard changes to look at maybe climate influenced hazards in the future, then I think that also opens up a huge box of questions as we're looking at deep uncertainties. And so I think having a space to explore those without having to be the expert in every piece is helpful for our community.
Yeah, and I agree with all that my colleagues mentioned earlier. And I also point to, I think, to an earlier comment by Alex that the scope of some of the works we do for our own projects, it might be different from what SimCenter is looking for. For example, methods that are applicable in general, they're stable and working in all circumstances, while our applications in a particular research might be about a particular problem with a particular setting. So that's something that must be considered in such collaborations. And one challenge that also Paulo brought up is the bandwidths for doing those kind of collaboration, to take a model that we have developed for a particular application to a platform that is for general purpose application within UQ. But I think that's a important task, however, and I hope there are ways to support the efforts. And I think the staff and researchers at SimCenter, to the extent I know, are very open and collaborative to facilitate that. So that's a great thing about SimCenter.
Yeah, I think in summing up, I think the regional risk assessment will gonna be one of the next frontiers in natural hazards engineering, and especially, and there are two aspects. One is the probabilistic modeling itself, which is important, and I'm not gonna downplay the importance of uncertainties, but that's a separate discussion for me always, because UQ comes after that. And after we have figured out what are the probabilities, the uncertainties, how do you efficiently propagate them? So that is the key role that UQ has to play. And of course, as Paul also said, like, you can sort of reverse the role and help define a little bit better those epistemic variabilities using UQ tools. I'm gonna share my slides to wrap up these discussions. First of all, If you're interested in these topics, there is a mini symposium that in 2 different conferences in 2025. The first one is EMI Mechanics System Conference in May, and the other is the ICOSAR in June that the 4 of us have decided to co-organize. And then the SimCenter has a number of these roundtable discussions organized by different working groups. We were the first ones here at the top, and then there are going to be 4 others on different topics, some closely related, and you can see there is a common theme on all of them. They try to look at the regional simulation, sort of the simulations at the regional scale, and you can find more information directly going into the link that I have here at the top. With that, this concludes the Q&A and the presentation, the Q&A session of this roundtable discussion. So now we're gonna, with the help of Matt, we're gonna open I think we're gonna stop the recording, and then we're gonna open the floor more broadly